What do you think might have been different, Jeremy?
The soil?
Same soil, controlled variable. Tanner?
Did you give them only water?
What?
Did you give them only water?
Only water, both of them. Anybody think of anything else? All right. Here's something a lot of you may not know.
Is genomes?
Yeah. Oh.
Here's something you may not know. Green plant stems tend to grow straight up. Green plant stems tend to grow straight up. All right, that should give somebody a clue about how this was treated differently. Does that tell anybody how this might have been treated differently? TV?
Did you like?
Go ahead. Same soil, same water, same fertilizer. What do you think, Mason? What do you think I did differently?
Did you live then?
Well, you're on the right track. He's on the right track, Megan.
Did you put the water on only one side?
No, water was the same for both of them. Stevie?
Like, did half, you let it have sun for half of the week and then put a box over it?
Sun was the same for both groups. Mason was on the right track back there, but some of you may not have caught his clue. What do you think, Emily?
Did you turn the little thingy like other day?
The little thingy.
The
Okay.
styrofoam cup.
When I grew these, I grew both of these groups on my kitchen table. But I have this one growing like this. Did those stems grow straight up?
Yeah.
Yes, they grew straight up. That's how they were growing. So they were acting normally. Now, what are they reacting to? If they grow straight up, what is it in the environment that they're reacting to? It's one word. I only want a one-word answer. Tanner?
Sunlight.
No? Jake S?
It's cleverness.
Chase? No. Okay, look, it's the force that makes you go down when you jump off a chair. What is that force called, Stevie? Gravity. They were reacting to gravity. Green plant stems grow upward away from the pull of gravity. So these were doing what was normal. It's just that I had the container tilted. So what, in one word, what was the manipulated variable with this group? One word? Gravity. Okay. Now, here's group D. What you should notice about these is that they're a lot smaller.
Oh.
All right? So the problem in this case is why is D smaller? Look at the difference between them. Okay? Who wants to ask about a possible manipulated variable? Wyatt?
Did they get the same amount of water?
They got the same amount of water, controlled variable. Chase?
Did you plant them all at the same time?
Planted them all at the same time a week ago, controlled variable. But Chase probably knows that the later you plant seeds, the later they'll come up, right? Most of you know that. All right, Allie.
Did they get the same amount of sunlight?
Same amount of sunlight, controlled variable. Jonathan.
Did they have the same soil?
Had the same soil, controlled variable. Stevie.
Did you put anything on top of it?
Nothing on top of either one, controlled variable. Jeremy.
Did you,
What, Nathan?
Is the same amount of soil?
Same amount of soil. Megan?
did they get the same amount of sun?
Same amount of sun. All right, I don't think you're gonna guess, so I'm gonna give you a clue. I'm gonna write the 4 seasons of the year here, starting with fall, which is the season right now, winter, spring, and summer. You're gonna vote on which of these, as I name them, you have to mow the lawn most often. How many say you have to mow the lawn most often in fall? winter, spring, summer. Well, spring and summer are about equal. You have to mow the lawn most often in spring and summer. All right, now I'm gonna ask you to vote on the season when you have to mow the lawn least often. How many say fall? How many say winter? How many say spring? How many say summer? Well, if this was the first grade class, somebody probably would have voted for summer. Because first graders don't have the same sense of logic that fifth graders do. Okay. Well, so you have to mow the lawn more often in the spring and summer. Why? Why? That could be related to this manipulated variable. Janelle?
Because it's sunnier.
Not because it's sunnier. What else, Janelle, besides being sunny, what's true about summer? What's true about it, Jessica?
Oh, I just.
Besides summer being sunnier, what else is it, Brandon?
More things grow in summer.
Why? Why, Jonathan?
It's warm.
It's warmer
Oh.
in summer.
That's what it is.
And plants grow faster when it's warm. All right, now somebody ought to be able to name the manipulated variable for D. Megan?
It was colder. You put it
Right, I grew these on my kitchen table where it was 68 degrees. I grew these in my garage where it was 40 degrees. That's the difference in growth between 68 degrees and 40 degrees in 1 week. Plants grow faster when it's warm, slower when it's cold. Okay, so here's what I'm gonna write for the conclusion. 3 parts. B was yellow because it got less light. C was leaning because the container was tilted. D was smaller because it got less heat. All right, that's all you need. This is all you have to put on the front of your record sheet, but you're gonna put a lot on the back of your record sheet. I still have a lot to tell you that goes on the back of your record sheet. Be sure you put the rest of the information I give you on the back of the record sheet, because that's where I'll look for it when I grade it. Okay, write that down. And then I'm gonna write something else up here that's important. You're going to have to put these diagrams on the back too. All of this that I put here goes on the back. I'm going to draw a radish leaf cell, but I'll leave it up here after I leave, so later on you'll have time to copy it. Because I want you to listen to what I say as I'm saying it. Okay, the outermost layer of a radish leaf is a cell wall, just like on the potato cell. Cell wall is on the outside of all plant cells. Then inside that, we have this thin structure that regulates osmosis called the cell membrane. And then in here, we have the cell juice, water with dissolved salts and sugars. But there's one additional structure in the radish leaf cell that's not in the potato cell. Who can guess what color it is? Jessica?
Blue?
No. What color do you think it is? Chase?
Well, it's not about that,
Well, I don't want to discuss anything else at this point, Chase. What color do you think it is, Tanner?
green.
Huh?
Green.
Green. In the radish leaf cell and in all green plant cells, there are these little green bodies called chloroplasts.
Oh, this one, that last.
Chloroplasts. Who remembers what chloro means in Greek? What?
Green.
Green. Plast means body. Chloroplast, green body. Okay. So the radish leaf cell has these, and that's why it's green. The part of the potato you eat doesn't have the chloroplast, so that's why it's not green. So now you know about 4 main parts of cells, but you're going to learn a lot more parts when you take high school biology. The chloroplasts are where the chlorophyll is. Now what does a plant need to form chlorophyll? Mason?
Light.
Needs light. All right. I'm going to write up here the 2 most important chemical reactions on Earth, because our survival depends on these. The first one is photosynthesis. Comes from 2 Greek words. Photo in Greek means light, and synthesis means putting together. So this is the process by which plants put together things. Here's what green plants can do, and only green plants. They can take carbon dioxide out of the air and water out of the soil, and because they contain chlorophyll, and if the light is shining on them, they're able to make glucose, which is a very simple sugar, and oxygen. That's the chemical equation for photosynthesis, and it only occurs in green plants, and it's only made possible by chlorophyll. Chlorophyll is the only substance that can bring this reaction about. So that makes chlorophyll fairly important to us. It only happens in light. And by that process, the plants make glucose, which is the sugar that our cells need for energy. All of your cells need glucose as a fuel for energy. But the green plants, by the same process, make oxygen. All of the glucose for all of our energy comes from this process. All the oxygen we breathe comes from this process. So that makes this process very important. Without it, we couldn't survive. The other reaction is called cellular respiration, and this is going on in all of your cells right now. Cellular respiration. That's what's going on in our cells. We get glucose from the food we eat. We get oxygen from the air through our lungs. And we produce carbon dioxide. And water. Plus, the energy in the glucose is released by this process, and that's the energy that supports all of the activities of your cells. I don't expect you to understand both of these completely at this point, but I'm going to explain both of them some more, and I think most of you will understand it. by the time I'm done. I'll leave these up here, and after I leave today, you'll have time to copy them if you don't have time to copy them now. But it's important that you listen to the explanations I give you now, rather than copying these. Okay. If you look at these two reactions, you should notice that they're the reverse of each other. The green plants produce what we need, and we produce what the green plants need. So, for that reason, I call this the balance of life. I use the word balance because ideally they'd be balanced. Ideally, the plants would be producing as much oxygen as we needed. But we're upsetting that balance drastically. Green plants can do this. They can produce the glucose we need and the oxygen we need. But we're destroying green plants thousands of acres a day, all over the world. At the same time, we're increasing the number of oxygen consumers, the human population, by thousands of people a day. So the oxygen producers are decreasing, the oxygen consumers are increasing. What's bound to happen if those two trends don't stop? What's bound to happen? Anybody figure out what's bound to happen, Emily? What?
We'll all die.
Why would we die though? Why would we die, Stevie?
Because we wouldn't have any oxygen.
We'd run out of oxygen. If the plants produce the oxygen we need and we're destroying the plants, but we're increasing the human population which needs the oxygen, it's like money in a bank account. If you take out more than you put in, you're going to eventually run out. Now don't get frightened by this story, because even if all the plants stopped producing oxygen today, we probably wouldn't run out for 2 or 3 generations, because the atmosphere is 20% oxygen and it's 63 miles deep all around the Earth. So there's a big reservoir of oxygen there for us to use if the plants stop making oxygen. But if we continue to destroy plants at the rate we're destroying them, and if we continue to increase the human population at the rate we're increasing it, it's inevitable that eventually the Earth would run out of oxygen. Now, it won't happen in your generation, but it might happen in your grandchildren's generation or your great-grandchildren's generation. So for that reason,